Cause precedes effect. This principle appears self-evident. A glass falls, then it shatters. A signal is sent, then it is received. Events unfold in sequence, and the sequence appears fixed. Human reasoning depends on this ordering. Science depends on it. Law depends on it. Yet physics reveals that this ordering is not absolute. The distinction between cause and effect is not a fundamental feature of time. It is conditional. Under certain conditions, the sequence reverses. Under others, it becomes ambiguous. The universe does not guarantee that causes come before effects. It guarantees something narrower, something more fragile. Albert Einstein uncovered the mechanism that prevents causality from collapsing entirely. The explanation is not intuitive. It does not rely on common sense. It relies on a single constraint buried in the structure of space-time itself. That constraint is the speed of light. Without it, the distinction between cause and effect would fail. This is not a philosophical claim. It is a physical fact. The explanation follows. Human experience reinforces the belief that causes always precede effects. Every observable event appears to follow this rule. A stone is thrown, the window breaks, the order seems irreversible. No observer has ever witnessed a window breaking before the stone was thrown. This consistency shapes intuition. It creates the impression that causality is absolute. The assumption extends beyond everyday experience. Scientific reasoning depends on causal ordering. Experiments are designed to isolate causes and measure effects. Predictions are made by tracing forward from initial conditions. The entire structure of empirical inquiry assumes that the temporal sequence of events is observer-independent. If one observer sees A causing B, the assumption is that all observers see the same sequence. This assumption appears justified. In ordinary circumstances, observers agree on the order of events. Disagreements arise over interpretation, over mechanism, over relevance, but not over sequence. The sequence itself seems fixed. It seems to belong to time itself, not to any particular perspective. This confidence is not irrational. It reflects the structure of human experience, but it is limited. The structure of experience is constrained by low velocities, short distances, and weak gravitational fields. Outside those constraints, the assumption fails. Observers in different states of motion do not always agree on the order of events. Causality does not collapse, but it does not hold in the form that intuition suggests. Before Einstein, physics treated time as absolute. Isaac Newton's framework assumed a universal clock. All observers, regardless of their motion, agreed on the time elapsed between events. They agreed on simultaneity. They agreed on sequence. If event A occurred before event B in one frame of reference, it occurred before event B in all frames. This framework made causality straightforward. Causes preceded effects for all observers. No ambiguity arose. No paradox was possible. The temporal ordering of events was a fixed property of the universe, independent of observation. Newtonian mechanics reinforced this view. Forces acted instantaneously. Gravitational influence propagated without delay. If the sun were suddenly removed, Earth's orbit would change immediately. There was no causal gap, no propagation delay, no limit on the speed of information transfer. This picture was clean. It was predictive. It worked for every experiment conducted in the 18th and 19th centuries. The assumption that time was absolute seemed empirically justified. Observers could disagree about position, about velocity, about acceleration, but not about time. Time was the same for everyone. Einstein shattered this assumption. He showed that time is not absolute, it is relative. Observers in different states of motion measure different time intervals between the same events. They disagree on simultaneity. Under certain conditions, they disagree on sequence. The classical picture of causality built on absolute time could not survive. Special relativity begins with two postulates. The laws of physics are the same in all inertial frames. The speed of light is constant in all inertial frames. These postulates are experimentally verified. They are not speculative, but they have consequences that conflict with intuition. One consequence is the relativity of simultaneity. Events that are simultaneous in one frame are not simultaneous in another. If two events occur at different locations and an observer moving at constant velocity declares them simultaneous, Another observer in a different state of motion will not. One will see event A before event B. The other will see event B before event A. This does not immediately threaten causality. Disagreement over simultaneity does not create paradoxes if the events are independent. But what if the events are causally connected? What if event A causes event B? Consider two events. Event A is a signal being sent. Event B is the signal being received. In the rest frame of the transmitter, A occurs before B. The signal travels forward in time. But suppose an observer moves at high velocity relative to the transmitter. In some cases, that observer will see B occurring before A. The reception appears to precede the transmission. This creates a problem. If causality is absolute, causes must precede effects for all observers. But relativity allows event sequences to reverse. Either causality is not absolute, or something else constrains the reversal. Einstein did not abandon causality. He identified the constraint. One intuitive response is to redefine causality. Perhaps causality does not require temporal precedence. Perhaps the causal relationship is preserved even when the temporal order reverses. Perhaps the distinction between cause and effect is a matter of physical dependence, not temporal sequence. This does not resolve the problem. If an observer sees the reception of a signal before its transmission, that observer can in principle use the received signal to prevent its own transmission. The act of reception becomes a cause of non-transmission. A causal loop forms. The signal is transmitted because it was received, and received because it was transmitted. This is not a semantic issue. It is a structural contradiction. Another response is to restrict the definition of observers. Perhaps only certain frames are valid. Perhaps observers moving at relativistic speeds do not count. This is arbitrary. Special relativity does not privilege any inertial frame. All frames are equally valid. Restricting the set of observers to avoid paradoxes is not a solution. It is an admission that the framework fails. A third response is to deny the physical significance of event order. Perhaps the reversal is an artifact of coordinate choice. Perhaps the true causal structure is hidden beneath the appearance of reverse sequences. This also fails. Coordinate systems are conventional, but physical predictions are not. If an observer can act on information received before it was sent, the paradox is real. None of these fixes address the underlying issue. The problem is not definitional. It is structural. Relativity allows event sequences to reverse. Causality requires a mechanism to prevent causal loops. That mechanism exists. It is the speed of light. The speed of light is finite. It is constant in all inertial frames. It sets an absolute upper limit on the speed at which information, energy, or influence can propagate. No signal can travel faster than light. This is not a technological limitation. It is a structural feature of spacetime. This constraint preserves causality. It does so by dividing spacetime into regions that determine which events can influence one another. These regions are defined by light cones. Consider a single event. Draw lines representing the paths that light would take forward and backward in time from that event. These lines form two cones. The future light cone contains all events that can be influenced by the original event. The past light cone contains all events that can influence the original event. Events outside both cones cannot interact with the original event. No signal can reach them, and no signal can arrive from them. This structure is observer independent. All observers agree on which events lie inside or outside a given light cone. They may disagree on the time intervals between events. They may disagree on simultaneity. They may even disagree on the order of events outside each other's light cones. But they agree on causal structure. If event A can influence event B in one frame, it can influence event B in all frames. If A cannot influence B in one frame, it cannot influence B in any frame. This resolves the paradox. Events whose order can reverse are precisely those that lie outside each other's light cones. They are space-like, separated. No signal traveling at or below the speed of light can connect them. Because no signal can connect them, neither can cause the other. The reversal of their temporal order has no physical consequence. Causality is not violated. Events whose order cannot reverse are those that lie inside each other's light cones. They are time-like, separated. A signal traveling at or below the speed of light can connect them. One can cause the other. All observers agree on their sequence. The cause always precedes the effect. The speed of light does not merely limit the propagation of electromagnetic radiation. It limits the propagation of causality itself. It defines the structure of cause and effect. Without this limit, the distinction would collapse. Causality survives in practice because no influence propagates faster than light. This is not a small detail. It is the foundation of relativistic physics. Every theory consistent with special relativity respects this constraint. Quantum field theory respects it. General relativity respects it. Particle physics respects it. Violations would be immediately detectable. If a signal could travel faster than light, observers could use it to send information into their own past. Causal loops would form. Predictions would fail. Experiments would produce inconsistent results. None of this occurs. The constraint holds. The constraint also explains why paradoxes do not appear in everyday experience. Ordinary objects move slowly relative to the speed of light. Event sequences do not reverse under such conditions. Observers agree on causality because they inhabit the same causal structure. The fragility of causality becomes apparent only at relativistic speeds or across vast distances. Modern technology depends on this understanding. GPS systems correct for relativistic time dilation. Particle accelerators predict collision outcomes using relativistic mechanics. Satellite communications account for signal delays. All of these systems assume that causality is preserved by the speed of light. Cause and effect are not absolute. They are conditional features of space-time. They are preserved not by the nature of time, but by the structure of causal influence. That structure is determined by the speed of light. Einstein did not discover that causality is an illusion. He discovered that causality is fragile. It depends on a constraint. Remove the constraint, and the distinction between cause and effect collapses. Observers would disagree not only on the order of events, but on which events cause which. Paradoxes would multiply. The predictive power of physics would vanish. The speed of light is that constraint. It is not arbitrary. It is woven into the geometry of space-time. It defines which events can influence one another. It ensures that all observers agree on causal structure, even when they disagree on temporal sequence. This is not a limitation. It is a condition of intelligibility. Without it, the universe would be causally incoherent. Cause and effect survive because the speed of light does not permit them to fail.